Good morning, good evening, good afternoon. Welcome everyone to another episode of the YugabyteDB Friday. Sorry about the echo there. To another episode of our YugabyteDB Friday Tech Talk. If I'm not mistaken, this is our 130th episode. So this is about 2.5 years of weekly talks. I'm Kannan Muthukkaruppan. I'm joining you from Bay Area, and I'm one of the co-founders at Yugabyte. And it's my pleasure to welcome today the speaker for the topic, Tim Elgersma, who's a member of our database engineering team, works a lot on the query layer and our Postgres compatible distributed architecture and various subsystems there. And over to him, both to introduce himself and then talk about the topic he's going to cover today.
Yeah, so as Kannan mentioned, my name is Tim. I've been at Yugabyte for just over 2 years now and based out of the Hamilton, Ontario area in Canada. And yeah, I've gotten to work on some pretty cool things at Yugabyte, and bitmap scans are one of them. And yeah, I had previously written a blog post that came out a few weeks ago. And so you can check that out. I believe it's linked in the description of the video. And there'll be a link at the end of the slides as well to check it out if you're interested for a bit more. But yeah, let's jump into it. So bitmap scans on YugabyteDB are a way to optimize queries with and or. And yeah, let's learn more about what that is. So we'll cover in this presentation what is a bitmap scan, like when would you use one, how do they help, what kind of queries do they help with, and some additional features that we support for bitmap scans, as well as some things that aren't yet supported, and then finally how they interact with our memory usage in YugabyteDB. So we'll start with a simple example. This is a table of movies, and in this table, there's a name, a rating, and a director for each movie, and there's just 4 movies in here. And there's also, for each entry, there's a YBCT ID, which is just our internal name for basically just a row ID. And so we have also an index on movies on the rating and an index on the director of each movie. And so that associates every row in the main table has an equivalent entry in the index, and we can look up the key column and find its YBCT ID and use that to quickly look up the YBCT ID from the main table. And so we can see here, like the movie Deadpool appears once in the main table, and its rating appears in the rating index and maps to that row ID, and its director appears in the director index and maps to that row ID as well.
And Tim, maybe one question. So in this case, the row ID seems to be an implicit kind of internal thing that Yugabyte is generating. But I'm just wanted to call out that if there was an explicit primary key on the main table, is it fair to say that this row ID is constructed using the primary key itself?
Yeah, that's exactly right.
Thank you.
So a standard index scan on both Postgres and Yugabyte works quite simply. If we have this query like select everything from movies where rating is 8, then first we go to the index and we can immediately jump to the first row with rating equal 8, and we get the row ID for that. And then there's no more ratings that match, so we don't have to look up any more rows from the index. And then we'll go to the main table and we'll get that row. And so it's 2 quick and easy steps, and both of them happen quite quickly. But if we have a similar query, select everything from movies where rating equals 8, or the director, or it's directed by George, then we can no longer answer this just using one index. We'd have to use both indexes somehow, which Postgres does using bitmap scans, or we'd have to just give up on using indexes entirely and scan through the main table. So without bitmap scans, that's what we had to do, and it was not ideal. So for every row in the main table, we'd have to look through, was this directed by George or have a rating of 8? And yep, it does. this one doesn't, this one does because it was directed by George, and this one doesn't. And yeah, that's not too bad when there's only 4 rows in the table, but if there's millions or hundreds of millions of rows, this can take quite a long time. So with bitmap scans, if we set this flag YB enable bitmap scan equal true, then that same query will do 3 steps instead of iterating through the whole table. So first we'll access each index to get the YBCTIDs or the row IDs, and then we'll combine the YBCTID sets together, and then we'll access the main table to get the rows. So first we'll create a bitmap set for this rating index, and we'll go to the rating index and find the one row that matches is rating equal 8 with YBCTID ABC123. So we insert that into the set. And then we'll create another bitmap set for the director index. And the one director that matches is George Miller. So we'll put that row ID into this bitmap set, GHI789. And then because we have an OR condition here, we'll combine these two YBCTID sets with a union operator. So we union them, and now we have one set containing 2 row IDs. And finally, we'll go to the main table, and we can look up those 2 rows. And yeah, so let's jump into, yep, do you have a question?
Yeah. So, Tim, like maybe some comparison between, maybe the Postgres's way of doing things, like, and maybe even some insight into why this is called a bitmap. Why the word bitmap, but it doesn't quite apply in Yugabyte case. I don't know. Would love to hear your take on that.
Yeah. So the overall idea of this is very similar to what Postgres does, where like these steps are the exact same, except they call their tuple IDs TIDs rather than YBC TIDs. But yeah, so we'll go to each index and get that set of IDs, and then they just store them in a different data structure. Because Postgres' storage layer is integrated with the query layer, it can know a bit more things about how everything is laid out. And so it can store things in a slightly more efficient data structure. But basically the idea behind a bitmap is like you can kind of think of it like a great big array with one entry for every row in the table. And a bitmap would set like one in that array for each corresponding row that you need to select. But even Postgres doesn't do things quite that efficiently because millions of rows equals a million entry array, which is not ideal. So Postgres still has a slightly more sophisticated data structure than that. But yeah, the data structure is different between Postgres and Yugabyte because the underlying storage layer it represents is different, but the overall flow of the ideas is the same.
Yeah. So I think what you're saying is in their case, these sets are actually represented using bit maps or bit arrays of zeros and ones that may represent either specific rows or pages. And while the concept is the same, in our case, it's not exactly a bitmap, but nevertheless, so as to not confuse the users when they see an explain plan output and so on, we've kind of stuck to the same terminology of a bitmap scan.
Yeah.
Yeah. Thank you.
So yeah, let's jump into a little example to see this in action. So I have a table here that's quite similar to what I showed in the slides. We have a table of movies with a name and a rating and director, but I've also added a release date column, and we have indexes on each of those 3 columns. So each of these columns has an index on it. And if we just perform a simple index scan, I can run this and I'll say, give me the name of the movie where the rating is greater than 9.9. And that's gonna first go to the main or to the index, the rating index, and it's gonna read through 41 rows from that index. And then it's gonna go to, or get 41 row IDs from that index. And then it's gonna go to the main table and get the name corresponding to each of those row IDs. And that's similar to what we saw on that first slide of the presentation. But then we can apply another filter. So we want here, give me the name of the movie where it was released in the month of June, and its rating is greater than 9.5. So what we're going to do here is use the release date index, and we're going to read 2000 rows from the index. And then when we go to the main table, we'll apply a filter to make sure that each of the rows that we've retrieved also have a rating above 9.5. And so that's a relatively simple and easy way to apply an AND filter. But with an OR filter, we can't do that. So I'll set bitmap scan to false. And if I run this, it's that same query as above, but with movies released in the month of June or rated above 9.5. And here we have to perform a sequential scan, which takes a very long time, 200 milliseconds to return these results because we had to scan 1 million rows from the main table. And yeah, but if I run this same query with bitmap scans enabled, then you can see we perform a bitmap scan here, and it took 18 milliseconds instead of 200 milliseconds. And what happened in this? First, we launched a bitmap index scan on the release date index. So we're looking for rows matching this condition, and we found 2000 rows that match that condition. And then we launch a bitmap index scan on the rating index, and we find 1300 rows that match the rating condition. And then because we have an OR operator, we'll union those two sets together and end up with 3300 rows. And then we'll go to the main table and we'll look up the rows from there. And yeah.
I think the other aspect you can see is for those 3,300 rows, they were not 3,300 individual requests at the lower layer. Those are batched, and in this case, those were done over 4 batches of requests. These could be to 4 different servers because it's a distributed architecture. Yeah.
So that's a simple bitmap scan, and we support bitmap scans for LSM indexes, which is the default index type for primary keys and secondary, primary keys and secondary indexes in Yugabyte. And we support both the heuristic and cost-based optimizer. So there's a Yugabyte Friday Tech Talk you can watch to learn more about the cost-based optimizer, I believe, and a blog post. But basically, we try to do the right thing and the smart thing in all situations, whether we know very little and we have to rely on heuristics, or we know a lot and we have some statistics to outline what we should do. And then we also support storage filters and aggregate pushdown. So let's look at what I mean by storage filters. And this is also, there's a Yugabyte Friday Tech Talk that came out a while ago about storage filters and expression pushdown, which could be worth a watch as well to learn more. So I'm going to take the same query that we ran above. So all the movies released in June or rating is greater than 9.5. And we can see its execution plan here, like 16 milliseconds. And I'm going to add a condition to the end. So every movie that was released in June or rated above a 9.5. And each of these movies, I want its day of the week to be, I want it to be released on Sunday. And so we can see what happened here is, I'll just zoom out a little bit so it fits all on one line. Yeah, Kannan, what do you see different between these two query plans?
Yeah. So basically, you're saying in addition, you added a condition to make sure like the day of the week was a Sunday. So I do see that there are 2 branches. One branch trying to get from the index based on the release date, and there is a storage index filter that has been additionally pushed down, presumably to restrict the number of matching rows we need to get, right?
Yep.
Um, but then the other branch could still give us movies from ratings greater than 9.5, but on that branch, the same filter is not pushed down, and that index may not even have the day of the week column, so we cannot apply the push down at the index layer. So we'll have to repeat the filter after doing the set union also. So I see that that filter is redone. But yeah, this makes a lot of sense that we are pruning as much as possible from every branch of the index we are trying to get potential candidate rows from. But in some cases, because not all branches have respected that filter, we have to reapply that filter. And presumably it's fair to say that a lot of this mirrors what Postgres does, and we inherit a lot of that by using Postgres as query layer as our building block.
Yeah, exactly. And because we were able to prune out some of these additional rows up here in this step, that meant we had less rows to send over or less row IDs to send over the network, and less row IDs to store into a bitmap and or union with other rows, and then finally less rows to look up from the main table. And so we can see this query up here without that additional filter took 16 milliseconds to execute, and the query down here with the additional filter took 9.6 milliseconds. So we ended up saving almost half the time because of this extra push down filter that we could apply.
Yeah, that's awesome.
Yeah. And we also support aggregate push down. So if I take this same query and instead of selecting the name of the movie, I'm going to select just the total count of movies that match these conditions, then we can see there's this partial aggregate is true in this scan node here, and then finally a finalized aggregate. So what's happening is the bitmap index scans are all executing as normal, but then when we finally get to this bitmap table scan, rather than needing to read 500 rows from the main table, we can just send a request for partial sums. And we have to request partial sums because there's different nodes and different data could be on different tablets throughout the system, but we'll request like a partial sum and then finally put together those sums at the end. And we only had to then transfer 6 partial sums over the network rather than 500 rows and count those rows. And
I see. Okay, got it. So maybe there were like 6 tablets or something, and so we are able to just do the local counts and then do the final count of counts. Okay, great.
Yeah. And yeah, so that's kind of some of the cool things we do support with bitmap scans. Things that we don't support yet are all tracked in this tracking issue that you can check out to learn more and like how we're doing with bitmap scans and what's coming up next. But we don't support yet GIN indexes or distinct pushdown. And there's a Yugabyte Friday Tech Talk you can watch for distinct pushdown as well. But that optimizes queries that have a distinct clause in them. And we don't support parallel bitmap scans. And we also don't support bitmap scans that exceed working memory. And so what do I mean?
And just to call out, like when Tim says we don't support GIN indexes, he again means it in the context of bitmap scans. But as a standalone, and outside of bitmap scans, GIN indexes are supported in Yugabyte. I just wanted to clarify that.
Yeah. And there's nothing too hard about supporting GIN indexes for bitmap scans. It's just not the highest priority right now. But yeah, it should be relatively simple because everything else is already set up. And yeah. So efficient bitmap scans that exceed the work mem limit that we have set in Postgres. So what's that? So Postgres has a variable called work mem that limits how much memory we can use in a slide or in a
session
query.
Like how much a Postgres connection backend is allowed to use as working memory.
Yeah. And so it might like write some temporary information around and like store things, and generally that should all be bounded by 4 megabytes. But bitmap scans work a little bit differently. So in vanilla Postgres, and we've copied this behavior in Yugabyte as well, each bitmap is limited by workmem. So you could have multiple bitmaps at once where each one is like close to workmem, and so you could end up with more than workmem memory being used at one time. So if I have this example query, like select everything from the table where K1 is less than 100 and K2 is less than 100, that might give me a bitmap scan plan that looks kind of like this, like bitmap index scan that selects 3 megabytes of row IDs and another bitmap index scan that selects 3 megabytes of row IDs. And when I intersect these two sets of row IDs, I'll end up with something that's between 0 and 3 megabytes in size. And so if we call that like roughly 2 megabytes, that works out and we can fit that in workmem. So even though at this point we had 6 megabytes worth of row IDs stored, we still didn't count this as a failure, count this as exceeding workmem, because at no point did we have a single bitmaps that exceeded workmem.
Got it.
But similarly, if we take the same example, but instead of and we have an or, then we have 2 3 megabyte bitmaps, and that's allowed. But when we union these, we'll end up with something that's between 3 and 6 megabytes in size. So if we call that like roughly 5 megabytes, then that exceeds workmem. 5 megabytes is bigger than 4 megabytes, and so we can't fit that into workmem. And so at this point, we would give up and stop executing a bitmap scan because we've exceeded workmem. And yeah, so what happens when we give up, when we can't store all that information into workmem? So if I take this query where I'm running a bitmap scan. So I'm running a bitmap scan, selecting all of the movies released after June 1st, 2024. And that runs perfectly normally. We're reading 8,000 movies. But if I change this so that we're still using a bitmap scan, but instead of 2024, I'm selecting everything from 2020 on, then we get this notice printed, exceeded workmem, switching to full table scan. And again, exceeded workmem printed in the explain plan as well. And yeah, so what happened is we were reading rows happily from this index and reading rows happily from this index. And then all of a sudden we realized that we hit workmem, and like once we started unioning these two sets, or while we were reading rows from here, we hit the workmem limit and we couldn't proceed with the bitmap scan anymore. So that's when we printed this log line, and then we threw away all of the work we had done so far. So we collected lots of row IDs, and those all had to be discarded. And then we just revert back to a full table scan, as it says here. So we do a sequential scan, but because we have these filters here that would have been implied by the bitmap index scans, we can still push down those filters for the bitmap table scan, or for the sequential scan. So we don't have to like fetch everything and then evaluate these filters locally. We can still push down the filters. And so the plan changes a little bit to not be quite as terrible, but this still executes much slower than a full sequential scan on its own would, because we waste time.
So there was a very relevant question here, like as you just spoke about, looks like here the query planner decided it's going to use a bitmap scan, but only at runtime it found that we're going to exceed the work mem, and it had to kind of throw away some work and switch to the other mode. And maybe it's not an issue in practice if mostly the queries are well tuned, but the question is related to would things be better if the cost-based optimizer, which is another capability that Yugabyte has recently added in the product, so would that have helped make a better plan judgment upfront itself, saying is the bitmap scan more suited, or should we just default to a sequential scan if we think the number of rows that the bits maps are going to have is large? So thoughts on that?
Yeah, so I actually have the cost-based optimizer enabled right now, just so that we use the optimal indexes for each thing. But if I disable it, then we'll probably use a bitmap scan here and exceed workmem. And that's because the heuristic-based optimizer, which we're using now, doesn't really know anything about row counts. And so it tried and it failed. And if I enable the cost model, then the same query will use a sequential scan because it believes we're going to be fetching too many rows for us to fit into workmem. And so it shouldn't bother
And had
wasting
you
that
already
time.
run the meaning had you already run analyze on the table?
Yeah, I had.
Okay. So you had run analyze, you enabled the CBO to use the cost model, and now it's able to upfront make a decision that if it is too many rows, like from 2020, then let's use this. What happens if you change this to 2024, and does it?
So 2024 is actually, it still believes that it would be faster to do a full sequential scan than, not because it believes this would exceed workmem, but because it believes it would be faster to just iterate through the whole main table rather than reading 20,000 rows from the index and then 20,000 rows at random from the main table. The sequential access of a sequential scan is still better. But if we change this to like a smaller amount, like June 1st, then it'll decide bitmap scan makes more sense.
Got it. So it is out basically it like how big is the table, how many rows it might fetch, and all that. So yeah, that's good to see that it's making a different plan selection based on that heuristic. So on like the number of rows and cost and so on. So excellent. Yeah, thank you. I think that answers the question, Tim.
Yeah. Yeah, there's a lot of cool cases in bitmap scans that the cost-based optimizer gets to cover, and it's cool to think about them all and where to apply storage filters and storage index filters and how much rows we believe will be returning, and if that makes more sense to use a sequential scan or if we might exceed workmem. And yeah, lots of interesting cases to think about. But yeah, that's what we do when we exceed workmem right now in Yugabyte. And yeah, that's it for this presentation. You can check out Yugabyte on GitHub or join us on Slack and ask any questions you have there. And you can also check out the Bitmap Scan blog post that came out a few weeks ago if you want to learn a bit more or dive into a bit more details about what bitmap scans are.
We are right on time. It was a wonderful presentation, Tim, and also just wanted to call out the amazing work you did on developing this capability itself in YugabyteDB. Highly recommend folks to read the blog to get a little bit more in depth into this capability. And yeah, thanks all for joining us on another episode of the Friday Tech Talks. Was one more question coming in? Which release of Yugabyte will this be generally available?
Yeah, so this is in early access now in 2024.1.3, but it'll be generally available in 2024.2, which should be coming out in the next few months, I believe.
Yeah, it's like 2024.2 is like the second release of the year 2024, which will generally be towards the end of the year. So yeah, so not too far. Also wanted to hand it off to you, Tim, for final remarks.
No, just try out bitmap scans, and if you like them, that's great. And yeah, feel free to reach out with any questions you have about them in the Slack channel.
Great. Thank you all for joining, and see you all on another episode of YugabyteDB Friday Tech Talks by engineers for engineers.